Welcome to Pigeon River Farm, doing farming right. I'm Robert Brown, the owner of Pigeon River Farm. Thank you for viewing. Well, good evening. In tonight's episode, we're going to discuss the next installment here of the build on a hybrid tractor. And what we've achieved to this point, I'm going to go over a lot of the details of what I did and the processes that took place. So the major accomplishment, we're at about, I could say 95% of all the high voltage, high current cabling is now completed. We have got the motor temporarily, as we'd say, still got some routing to do there, locked in. I have all the batteries are now in play, other than we don't physically have the last hookup, so the system is safe, so you don't have to worry about me getting electrocuted at this point. So everything, even to here, we do have one separation point in the circuit. So with that said, I started running in. Remember, the cables we put on here are 2/0 marine gauge cables. So I went with a high quality copper, very weather resistant as far as in climate, chemicals, all that. Extremely high grade. So the goal here is to have the least amount of voltage drop as possible. With the calculations, we should be running at darn close to 0 voltage drop throughout the whole circuit under a moderate load. Under a severe load, of course, it's a linear relationship. I feel pretty confident with going that style cable, that quality of cable. So, well, we were able to do that. Batteries all hooked up. The hardware I used when we got to the termination points here was I used a high quality stainless steel bolt, a bronze washer, and then we went with a high quality stainless steel star washer to get penetration on the surface area of the cable itself. And then everything was torqued to specifications. Now, I had looked up the specifications based on the bolt design and the fastener type. So unlike the batteries, I had to come up with my own spec for that. So again, that's something that's very critical. That will be something that will be maintained, and the torque will be checked because of the heat and vibration. The next thing that was critical, and we had to figure out the mounting configuration, and we had to figure out how is everything going to sit. And there's 1,000 different options for that. So a lot of time and playing around had taken place, and finally come up with this pedestal design with a flange in the back here for all the wire penetration. For any of the holes that ultimately will not be used, we'll simply put a sealed plug on there. So we want to make this as weather tight as possible. The key there is trying to have it so we can get everything in here comfortably. The last thing that's going to happen is actually then put on the cover that will weather seal it from the environment. That's a little ways out, but this pedestal was specifically designed with the heat sink in mind. So there's a very large heat sink underneath here. As you can see, in mounting it, there was a lot involved. So I actually took this plate and I had to do preliminary lay out the components as I thought they were going to fit, and then the process started. I had to take it, measure it, double check my measurements, went over to the drill press, and I drilled, and I actually used all the fastener here are 1/4" 20s. So I actually went ahead and I pre-drilled the aluminum plate. I threaded carefully. Now, if you haven't threaded aluminum before, it can be a little bit problematic as far as the tap filling up with the aluminum material as you're making the threads in there. So make sure repeated cleanouts are critical so you don't damage the very threads you're trying to produce. So getting that in place. The next one was very critical, the position of the controller in relationship to the heat sink. You can see I've got a very large heat sink that's here, and that heat sink has to have a perfect mating surface and be torqued down appropriately. So what I had to do is for the top side of it here, I simply drilled in 4 retaining holes, threaded, and it went with the right length of bolts. Where the heat sink went on the bottom, that had to be countersunk. So I simply drilled a hole, and then there was bolts that threaded into that housing itself. Because it was a used component that I was able to acquire, it came with metric fasteners in there. Not that that means anything, but I went ahead and I drilled to the appropriate size, and then I countersunk the heads of the Allen cap screws that I put in there. By doing that, they are just below the surface. I want to keep that to a bare minimum because the heat transfer was critical. So drilling, as you can see, we went ahead and we did all this drilling, the countersinking, attaching it, and now that the heat sink is there, before we attached anything, I used thermal grease. And thermal grease was absolutely paramount to the situation here. Otherwise, corrosion will build up. We will actually get a poor thermal transfer. So I had to apply thermal grease to the heatsink and thermal grease to the controller. So if you ever do build anything like this or plan on duplicating what I'm doing here, kind of pricey, but is absolutely imperative that you apply that. The next item was to mount, I guess we'd say, our low voltage, low current controls. And we got a circuit board. It's under development right now. I've got the physical board back. It hasn't been populated yet. That will be the next series of videos where we get into that detail. But that's going to simply mount right here. And then we're going to leave room open and for easy removal, and except because I'm going to have to put relays in here. Might be putting a thermal sensor. So there's a variety of different things that are going to go onto this board. It's currently not tightened down. And then we get into the high current relay. So this relay is intended to take the 144 volts that are going to come through here. It's kind of the main business end of it. So this is the safety. This is going to allow me to get going. It will be controlled indirectly. I would say directly, maybe it'd be a better way of saying it, from the controller, but then I'm going to be controlling the controller, and I will have an intercept. So I want to have multiple safeties on this so we wouldn't get in a condition where the relay shorts out because of a control related problem. And I got to make sure that I don't, because there's 2 things that can happen here. One is the relay could get stuck on, or one is the command could get stuck on to put on full power. I don't want to have either one, so I want to have an emergency override, and it's going to be simply controlled on the low voltage, low current side. So the reason I'm doing that is I really don't want to get the 144 volts outside of this controlled area and run long cables up. So I'm going to trust with the confidence here of that these 2 ways of controlling through the controller would have to go back to a 0 load mode, and I'll go into that in the next video in much more detail, and that the relay could be opened up and controlled. And then last but not least, the earlier discussion in a previous video, we talked about the decision to go with a belt versus a chain. I do have an ultimate slip factor here, so full power of this motor with that amount of battery at that voltage could never be applied to the tractor. So that another safety factor that was built in. Maybe down the road we find that this works very well, we don't have any challenges, I may switch over to a chain at that point. But as of right now, we're going to stay with the belt configuration. So the aluminum back to the mounting itself. So we went with aluminum plate. We got our brackets that got attached here. They mount to the fascia of the tractor frame, as you can see. And it all is modular and can be taken disassembled. Since I've worked in the service industry my whole life, along with farming, I recognize the importance, the absolute imperative that you have serviceability. You know, you're still going to have some challenges because you end up with a certain amount of real estate here that's going to be confined. But my goal here is to make everything as serviceable as possible, and even from a troubleshooting standpoint. So this is a prototype design. As we know the story on this, we want to get the prototype portion kind of out of the way here, get it into the testing mode, and then by next spring it should be thoroughly tested out, and we'll start the field applications at that point. So again, from the top, we've got the high voltage, high current cables all routed. Actually, the routing was kind of interesting. I know I showed in a previous video, but we have the chase that goes from one battery bank to the other, and then I simply went out of this battery bank here. I brought it over, and that's the area that's coming up next to the engine. And there I put on a sealing material. It's a chemical resistant, high temperature sleeve that goes over the top of the cable itself. And then, last but not least, and it hasn't been done yet, for anything that cables that are going to be exposed, we'll get a orange wrap indicating they are high voltage, not simply black and orange, or black and red, excuse me, and not have this on there, because this is one of the requirements for high voltage. So anything above 60 volts, you know, the rule is that we need to mark them as high voltage. So we'll be putting this wrap here on all the exposed cables to inform everybody that this is a high voltage environment. On the next video, we'll be talking about the controls as they start to populate. This is my throttle control. So this will be hooked to a hand throttle that will be basically a parallel circuit to for the gas engine throttle. And then that will come out here, and that will be the input signals to the controller, and that will be kind of the business end of it. I'll go much more detail in the next video. Well, I hope this information was valuable, and I truly appreciate your time and energy that you put forth in listening to this video, and I appreciate it, and you have a great evening.